All right, and we should be recording. Go ahead.
Okay, great. So welcome everybody to the ECP 2022 edition of the Spack tutorial. I'm going to share this screen. We only have a half day today, so we're not going to get to as much as we usually do. But I think we'll cover enough for folks to get an introduction to Spack if you've never seen it before. And then we have a developer workflow section at the end for folks who maybe have seen the tutorial before. So I'll show the schedule in a minute. If you are following along with this tutorial, everything that we're doing here is at spacktutorial.readthedocs.io. So if you go there, the page looks like this. You can download the slides that we're going to use, and you can follow along with all the exercises. Basically, everything is a script in one of these sort of submenus here. And we're going to be using Slack for questions. So go to Spack Slack. It's slack.spack.io if you don't have an account already. And once you're there, join the tutorial channel. And that's where we can take questions for this. We create it every time we have one of these tutorials, and then we let people join there. The other thing that we're going to do there is we have a bunch of Amazon instances that we're going to use for the tutorial. So if you get there, then say that you need an instance, and someone will give you an IP and a login so that you can get started on the instances. We're not going to do hands-on until after this intro section, but this is how we're going to be distributing logins. So definitely go there. All right. Is anyone? I guess if anyone's unable to do that, comment in the chat, and we'll get it sorted out here on Zoom. But I suspect people can pretty easily log in. Any questions on that before I move on? Okay. Give people a minute to go and join. Okay, if you missed this, or if you haven't joined yet, the instructions are down here at the bottom of all the slides, so you can see the URL and the Slack URL down here as well. So you can always look down here if you haven't gotten to this yet. All right, so today we have 4 presenters. We're all from Livermore. We've got Greg Becker, who's done this a bunch of times before, along with me and Tammy. And we have Rasharda Butler, who's relatively new at Livermore. She's been there for about a year, and she's going to do the basic section today. So we're really excited to have her give one of these tutorials today. And for the agenda, like I said, we only have a half day. So we're going to do this part. So this is the intro that we're in right now. There's a basic section that Richard is going to do. I'm going to do the core concepts part after that. This is sort of the talk. The basics is hands-on. We'll have a break from 11:30 to 12. These times are Eastern, by the way. And then we're going to cover environments. And actually, we were going to do configuration like the usual first half of our tutorial, but we've swapped it in for developer workflows. So we're going to skip the traditional configuration section and just go straight into dev workflows for the last 45 minutes of the tutorial. So we're trying to sort of mix up the amount of beginner and I guess intermediate stuff that we have. If you want to do more than what we have here for this tutorial today, there's a bunch of other sections that we would usually do that are on the website. So if you go to this website, spacktutorial.readthedocs.io, you can actually continue doing the tutorial. There's a packaging section. There's a section on mirrors. The configuration section that we're going to skip today is there. Stack scripting, and then there's some more roadmap stuff in the slides that we'll be able to cover today. Okay, so why do you want to use Spack? Most scientific codes rely on lots of dependency libraries. And so, for example, MFEM, which is a relatively small package, it's 31 packages, including all of its dependencies. So here's MFEM, and here are all of its dependencies, sort of under the water here. There's 69 different dependency relationships in that graph. LBAN is a bigger package for neural networks and machine learning for HPC. It has 71 different packages, and they have 188 different dependency relationships among each other. And then things get even bigger than that. If you look at like the R ecosystem, here's R-Condop, which is some sort of gene data analysis tool, which is 179 packages total, and there's 527 dependency relationships in there. But you know, the ECP is even bigger than that. So if you look at ECP's software ecosystem, this is E4S. This is the whole thing actually graphed out. The red parts in here are the around 100 packages that are in ECP ST. So that's all the stuff that we're working on. And then all these little blue dots down here are the things that you need to build the stuff that's in the E4S. So it's a huge ecosystem, and it's infeasible to build all this stuff and integrate it manually. So we use Spack to do that. And it automates the build, it automates software integration, and it parameterizes the build so that you can pick how you want to build these things so that we can install the same software stack across lots of different machines. If you look at other package managers, you can start to see why we wanted a tool like this. Oh, sorry, is there a question? No, okay.
Random background noise, apologies.
Oh, okay, nope, it's no big deal. All right, so if you look at other package managers, there's some fairly common assumptions that they make that make them sort of a poor fit for the way that we deploy software in HPC. So for example, with like RPM or Debian, you've got a one-to-one relationship between source code and binaries. So you make a recipe, you build the binary for that thing, and then you have one binary that you can deploy, and it's portable, it works across platforms, but it's not optimized. And so the desire to make these binaries as portable as possible is bad for performance. And they only really let you have one version of every package installed that's sort of designed to be upgraded over time. Whereas for scientific software, we often want to build the same package with different APIs, with different BLAS implementations, with different versions of dependencies, different compilers, different flags, and so on. So that restriction is pretty strict. And also, you want sort of a closer relationship between the source and the actual installed package. We're often hacking on the source, or we're often modifying the code as we install it. So having just a pure binary package management system is pretty restrictive for HPC. And again, the other thing with most distro package managers is that there's like one OS compiler. So for example, most distros like RPM and Debian are built with GCC. Your Mac is built mostly with Clang. They don't let you use the fancy vendor compilers or swap in compilers with new capabilities to build your ecosystem. So we're trying to solve these problems in Spack. In HPC, things are pretty different. People distribute code as source, with the exception of, say, vendor libraries and compilers that are on the system, and we also want to use those. So we want to integrate source builds with external packages. We often build lots of different variants of the same package, like I said, so different options and compilers. And we want to optimize the code for the processor and the GPU. So there's even more of a sort of close relationship between the code and the particular hardware that it's running on. We want to build something for the GPUs on the system. So all these DOE machines here have GPUs, and even on the ARM machines at Recon, they're ARM machines, but they have SVE instructions. So you want to make sure that you're optimizing for the vector units on machines like Fugaku. We rely heavily on pre-installed stuff. So we want to use the system MPI because it's tuned for the system. We want to use system GPU libraries, especially if they're proprietary and come from the vendor. And there are lots of languages in HPC. So we want to be able to integrate C, C++, Fortran, Python, and other things all in the same ecosystem. So with all these constraints, we need something much more general than a traditional system package manager. Containers are a good way to reproduce and distribute a software stack that you've already built. And people say, okay, well, if I have containers, why do I need a package manager like Spack? Somebody needs to build the container. And so even if you have a nice snapshot of your build of something, that enables you to distribute that build, but it doesn't really allow you to rebuild the container easily or tweak the recipe. And so the build itself is not trivial. So containers in Spack are really complementary. Spack lets you build the stuff that you want to put in your container easily, just like it would let you build stuff on bare metal easily. And the package manager inside your container is usually one of these OS package managers that's rather restrictive. So you can install a few things you might need, but for the vast majority of, say, ECP software or HPC stuff, you're going to want to build it from source to build your container. So yeah, so it smooths sort of the rebuild process for your containers, and it actually lets you write sort of more concise container recipes. So Spack's designed to enable software distribution for HPC. It automates build and installation. It can do source builds, it can do binary builds. So basically we call them build caches. We'll talk a little bit about that in the tutorial, where we're caching a particular optimized build. And the packages are parameterized, so users can tweak the configuration. So it's designed so that you can basically clone it from the Spack repo. So you go git clone, this is the Spack URL, and you can run Spack install right then when you pull it out of the repo and install HDF5. That installs HDF5 and all of its dependencies that it needs to run. This is sort of the simple case, but Spack allows customization. So you have this syntax that you can use on the command line to say, I want to install HDF5 at this particular version, or I want to install it with this compiler or with with this option. So doing some sort of thread option. I can pass flags to the build. I can specify a particular microarchitecture target. And I can do all that for my dependencies too. So if I install HDF5, I can say, nah, I didn't like the default OpenMPI. I want to build it with mpitch at a particular version. So you can test your software with particular versions of dependencies, which is a pretty powerful thing to do. We also generate modules. So if you want to deploy your software at a facility, Spack will generate modules for that. And you can actually customize how they're generated so that users can easily access the software without having to know everything about Spack. You can have environments, which we'll talk about today. And it has a lot of DevOps features built into environments. So there's things like continuous integration. You can generate containers automatically from an environment. You can run tests from an environment. There's all sorts of different things that you can do with Spack environments. They let you represent sort of a stack of packages as code that you can modify over time. So if you're wondering sort of what is a package manager, it's not a replacement for CMake and AutoTools. So if you've never seen one of these before, it's basically something that wraps around your build system and manages the relationships between packages, not the build for any particular one package. So Spack knows about the dependencies between your packages. If you say to install the root package in a large system, it knows that it needs to build all the sort of leaf nodes first, and it can build that whole graph bottom up until it gets to the top and builds the thing that you actually wanted once it has all the requirements installed. The other thing that it does is it's almost like a knowledge repository. So Spack itself is, we have over 1,000 contributors now who are working on these package recipes that represent how to build these different packages. And so that's sort of like a repository of all the magical configure lines and all the special things that you have to do to get packages to install on particular systems or to know which versions of external dependencies that they're building with. So yeah, you can think of it as sort of at the lowest level, there's things like Make and Ninja that really handle dependencies among commands and files within a build. High-level build systems like CMake and AutoTools sort of sit on top of that. They're designed to sort of handle the complexities of library management, and they have a few abstractions on top of make files. They typically generate make files or Ninja files to do their build. And then on top of this, Spack and other package managers are really tying together the relationships between lots of different projects in a larger software ecosystem. It's targeted at lots of different audiences. So Spack's really trying to span the gamut of HPC use cases. We want end users of HPC software to be able to use it. So people who just want to run software on the machines. App teams use Spack to maintain their third-party dependency libraries and to test their application with different versions of them. Package developers, people who want who are working on a package and they want lots of users to be able to use it more easily, use Spack. So they basically put packages into Spack. And then HPC facilities who deploy lots of software use Spack to actually get software on their site and to build sort of module hierarchies around it. The community is growing. So we have over 6,000 packages now. When we started in 2013, we had like none. And then when around the time of SC15, when we did our first sort of public presentation about Spack, I think we had around 170 packages. Since then, the lines of code has grown in packages, and you can see that we've gotten a lot of external contributions. So this is showing organizations that contribute to the tool. We've had over nearly 5,000 people contributing to or reading the docs at any given time. So in 1 month, I think we're actually up to close to 6,000 now for the number of people reading the doc site for Spack. And there's over 1,000 contributors to the GitHub site now. Oh, I guess I have this slide twice. Okay, here's the new revised version of that site with the right numbers. All right. It's used on some of the fastest supercomputers in the world, so including the top 3, so Fugaku, Summit, and Sierra. I think most people here are familiar with those, so I don't think I need to get into too many details about that. And it's critical within ECP, as I showed before, for integrating E4S, which is ECP's software ecosystem. So if you look at the dependence or the dependencies of projects, Spack has the most dependence of any project in ECP. It's not the most critical dependency because you could build any of these apps without Spack. You could just do it by hand. But for integration and for making the whole software ecosystem work together, everything is in Spack within ECP, and so it ends up being the most dependent upon thing. There's another tutorial going on right now about E4S, and so if you're interested in that, I don't know, it's too bad that they're scheduled at the same time, but I'd recommend watching the video of that after this one once you're familiar with the tool, because they have some pretty interesting use cases. E4S has a binary cache, and they allow you to sort of accelerate your installation and your CI for your project by easily using all the ECP packages. Spack development takes place on GitHub. So if after this tutorial you're interested in contributing, we have a really active community. We merge hundreds of pull requests every month, and there's lots of active authors every month who are actually working on things in Spack. So I think if you want to get into it, the community is pretty friendly. So get on there and submit a pull request if you want your package in Spack, or if you want to tweak something or make something better. We have a lot of contribution from industry now, both since Spack's been around a while, and also because ECP's had a big impact on this. A lot of these vendors are contributing versions of their compilers and their tool chains to maintain them in conjunction with different exascale collaborations around the big machines. We're working with AWS on CI for Spack. So there's actually Cloud CI where we're building things automatically in the cloud, and AWS is providing credits for that. So we have a lot of industry collaborations as well. But Spack's not the only tool that automates builds. There are other things you could look at. It was inspired partially by Nix and Geeks, which are sort of functional package managers. We'll learn a little bit about Spack's installation model, and you'll see why that is. We get the hashing that we do from these systems. We are a lot like the build from source package managers, like old school Homebrew before they went binary, and MacPorts and Gentoo. And then EasyBuild and Conda are probably the 2 closest competitors in the HPC space. EasyBuild is another from source build tool. It's more targeted at facility deployment, and it doesn't cover all the different use cases that Spack does. And they don't do things like binaries. Conda is binary only, and it's really popular for the Python ecosystem and for data science. But it's generally not really targeted at HPC, and it can sometimes be hard to get Conda to work with the MPI and the other libraries that are on HPC systems. So ABI compatibility can be an issue there. But check these out if you're interested in other things in this space. All right. So we're going to go to Spack Basics with Risharda next. But I'm just going to remind everybody before we do that to join the tutorial channel on Spack Slack. We'll be taking questions there. I think it works really well because of the threaded format on Slack. So go there and ask for a machine, and we will get you that so that you can follow along with Risharda for the hands-on portion of the tutorial. And again, all the tutorials are at spacktutorial.readthedocs.io. So we're going to go into the basics section next. Any questions on that, or has anyone been unable to get on Slack? All right, in that case, I will just hand it over to Risharda and see you all on Slack. And it's just slack.spack.io. So hopefully that's easy to remember. All right, thanks.
Good morning, everyone. I'm going to share my screen so everyone can see. Can everyone see my screen?
Not yet.
Okay. Looks like it's doesn't have access. Give me a second to do that.
Are
I
you in
can
the
make
Zoom?
you a co-host if need be.
Yeah.
Yes, I think that would help.
Right, you are now a co-host. Go ahead and try again.
You're not in the web app, are you, Misharda? Are you in the actual Zoom app?
I'm on Zoom on Chrome.
Oh, weird.
Let me see. Let's take a bit. Okay, let's try this again. Yeah, I can't seem to get it to allow me to share my screen.
Does it pops up the choice of things to share and you're able to pick something, but it just doesn't share?
Yes.
Weird. Okay. Let's see. So Greg, are you around?
Yes,
Yeah. Do you want to do the basics or you want me to do it?
I can do it.
Okay. I think we'll have to switch to me or Greg. Sorry, Risharda. That sucked.
Yeah.
Yeah. Okay, Greg. Why don't you try it and see if you can share? Maybe you can't share either. Let's see.
Yep. Just a second. Let me grab an AWS instance.
Okay.
Okay. And then let me grab the script for it. Okay. We're doing the basics section. All right. And now let me share my screen. All right, can people see my terminal and my browser side by side?
Yes,
Yes.
sir.
All right. So we're going to talk about some basic usage of Spack. You know, how do I install a package? How do I see what I've installed? How do I uninstall a package? And then we'll get at the end a little bit into how do I manage what compilers I have available. So Spack is designed to work out of the box. You clone Spack from GitHub, you can get going. We're going to do something a little more complicated to make sure that we're all using the most recent stable release instead of the tip of develop. So we're going to git clone https github.com, if I can type correctly, /spack/spack. And we're going to put it in our home directory. And from there, we could run Spack as soon as that finishes. But instead, we're going to check out releases /v0.17. That's the release branch for the latest set of stable releases. And make sure you do this step. The most common problem we have during the tutorial is people are installing from source instead of from binary, and it's taking forever, and it's because they didn't check out the version of Spack that we prepared the binary cache for. The next thing we're going to do is we're going to add Spack to our path. We could just add it to our path directly. That would work for most things, but there are some commands in Spack that have shell integration, and for that, we need to source the Spack setup file. So we're going to source share Spack setup-env.sh. If you're a C shell user, that would be CSH. Now we're good to go. We can run Spack list. It's probably the simplest command in Spack. It's going to just show us what packages are available. And it's going to take a second the first time it runs because Spack has to build up some internal caches of what packages are available, what packages provide what virtuals. We'll talk about what those things mean later. But we can see it's run through and we get this unhelpfully long list of almost 6,000 packages. In the develop branch, we're over 6,000 packages now. So we can also restrict that. We can say Spack list pi- and see everything with pi- in its name. This is our naming convention for Python packages. And we can also look for something particular. We can say, okay, I know I want HDF. How is that named? And we can see, okay, there's a separate package for HDF5 in Spack. That's maybe what we want. So that's the Spack list command. Not going to spend too much time on that because what we use Spack for mostly is we want to install things. So let's try it out. We'll say Spack install zlib. And Spack is going to take this abstract spec, is what we call it, zlib. We haven't said anything about how to build it. It's going to fill in all of the defaults for us. It's going to figure out that the most recent version is 1.2.11 and the best compiler we have available on our system is GCC 750. And then it's going to install zlib in that configuration. And you'll see it spent a minute bootstrapping Klingo. Before that, we use Klingo under the hood to make those optimizations. And Todd will talk more about how all of that works in the concept section. So Spack can install from source like we just did. Zlib installs from source really easily. We can also install from binaries with binary caches that are signed with GPG for security. And for the rest of the tutorial, we will install almost everything from binary just to speed things along. We don't want to have to wait for something to take 40 minutes to compile. So to be able to install from the binary caches, we're going to add the tutorial mirror, which is we have locally on all of these images to make sure the network isn't a problem. And then we're going to have to trust its GPG keys. So we're going to say Spack mirror add tutorial, and it's in /mirror. And we're going to say Spack build cache keys -- install -- trust. So we've told Spack about the mirror, and then the second command is saying, for every build cache you know about, I'm interested in its keys and I want to install them and automatically trust them. So now we're ready to trust the installs that we prepared for this tutorial. So Spack, a major component of Spack is what we call the spec syntax. And that's the interface that we use to say what spec we want to install, what aspects of the spec we care about. And the first thing we'll use from the spec syntax, besides just the bare zlib spec, is we're going to use the % sigil, and that's how we specify compilers. So we're going to say Spack install zlib %clang. We want zlib built with clang instead of the GCC build we did earlier. And so Spack's going to install patchelf. We use that to deal with the binaries. And we finished installing patchelf, and then we finished installing zlib. And you can see in the path, this is the one built with clang. It's important to note that this is installed in a fully separate path. You can see the compiler shows up, the version shows up, but also this hash. Todd will talk more about the hashes in the concept section, but this is what allows us to support arbitrary versioning and configuration of packages. And it plays a major role in how Spack is architected and also how we interact with Spack from the command line. So let's say we want a different version of zlib than we had. We're trying to reproduce some old software. We want 1.2.8. So Spack versions zlib. And we can see here at the top, we have the versions Spack knows about. We have checksums for those. We'll make sure we're getting the source we think we're getting. And then we can see here's everything else that Spack was able to find from zlib's website that maybe you could try out, but we don't have checksums for. And you can see 1.2.12 is newer than what we have available. In the develop branch of Spack, this is made available. It'll be in the next release. So if we want to specify a version, we use the @ sigil. So we're going to say Spack install zlib at 1.2.8. And there we go. It's real quick now that we're all set up for the binaries. Similarly, we use the @ sigil for compiler versions as well. So we can say Spack install zlib built with GCC at 650. So that's versions. The spec syntax also includes compiler flags. We accept all of the major flags that you would expect from things like AutoTools and CMake. And the values have to be quoted if they include spaces, pretty normal parsing stuff. And these compiler wrappers, by default, are injected into the compile line automatically by the Spack compiler wrappers. So you might not see them in the output the way you were expecting, but they would still be there. But different packages can have control over how that behaves. So let's install an extra optimized version of this old zlib that we wanted. So we're going to install zlib at 1.2.8 for version 1.2.8. And we're just going to say CPP flags equals -03. And there we go. So now we've installed a bunch of things, maybe too many versions of zlib, who's to say, but enough that we might not remember all of what we did. So we can use the Spack find command. And if we just use Spack find, some of these might appear identical. They differ in some other way that's not shown here. So we can use Spack find -L to show the hashes. And we can see, okay, these two zlib 1.2.8s are actually different. And if we remember, those are different because we specified the compiler flags for those. We can see the compiler flags if we say Spack find -F. So Spack find -LF, and we'll see all of the zlibs that we've installed with their compilers, their versions, their hashes, and their compiler flags. And we can see only one we set non-default compiler flags for. So we'll move into some more complicated software now with some dependencies, and we'll get to look at how you specify dependencies in the Spack syntax, and also how Spack reuses software. So we're going to install TCL. For those of you who aren't familiar with it, TCL is the language that many module files are written in. But for this tutorial, it's notable in that it is a package that has exactly one dependency, and that is zlib. And you can see when we went to install Tickle, the first thing we see is, oh, we have zlib already installed because it used the default concretization of zlib, which we already had installed. Now, we can request dependencies explicitly using the caret sigil. So we can say Spack install Tickle depends on zlib at 1.2.8% clang. So here you can see this spec syntax is fully recursive telescoping syntax. Anything that we could specify about a top level dependency, we could put on TCL here. We can also specify about its dependencies. So here we go. And now we had to build a new zlib for this and a new TCL. And you can see this new TCL we built was also built with Clang. So Spack is going to try, unless you really work to tell it otherwise, to use the same compiler for everything in the graph of your dependencies, in the directed acyclic graph, or DAG. So here we've used, or we've specified a Tickle build that required a new zlib. And before we had zlib around already and it was used automatically. So we can also request a specific build that we've already done by its hash. We talked about the hash a little bit earlier. If we run Spack find -LF again, we can see this optimized zlib that we built, with the preprocessor flag set to 03, has this hash. So if we copy that hash, we can say Spack install TCL depends on the thing with this hash. And we don't need to say the whole hash. We just need enough for it to be unique. If it's not unique, Spack will complain and tell you, hey, that was ambiguous. And so now we're reusing that zlib again, and we've built a new TCL on top of it. So now that we're dealing with dependencies, there's another flag for Spack find that we might care about. We can run Spack find, and we'll see we don't see any of the relationships between these. But if we run Spack find with -D, you can see for each Tickle, here's the zlib associated with it. All right, so that's very basics. Let's deal with some bigger software, something that we might care about installing, maybe something that depends on MPI. We're going to start with HDF5. So we're going to say Spack install HDF5. And so this is telling Spack, I just want HDF5. I don't care how you build it. Give me the default build of HDF5. And that's going to start blowing through a bunch of dependencies. And one thing that we'll notice is the MPI that we use in this case is OpenMPI. You can see it in the output on the right here, and you'll see it scroll by in the output on the left pretty soon. That's just the default in Spack. We'll talk in a minute about how we can swap that out if you want a different implementation of MPI. Okay, so here we've installed a bunch of stuff. Perl is taking a minute. It's a big binary to unpack. So it's usually a spot where we sit for a second here. So you may or may not be familiar with HDF5, but one thing notable about HDF5 is that it has options for whether you want to build with MPI or not. And we haven't really worked with build options yet, so that's the next thing we're going to focus on. Okay, here we are. We're all the way up to unpacking HDF5 now. You can see OpenMPI was the last thing before it. So we're going to talk about variants. So variants in Spack are options. They can be Boolean or they can be open-ended values, key value pairs. If they're Boolean, we have a special syntax for them. We use the plus to turn them on, and we use tilde or minus to turn them off. The reason we have two sigils for disable is because generally we want to be space agnostic, and we can be with the tilde. But tilde foo is going to expand to foo's user directory if foo happens to be a user on the system. So we have the minus sigil, which needs a space before it, but you can use that if there's a poorly named user, or not poorly named, but a user whose username is unfortunate for what you're doing at that exact moment. So let's actually use some variants. HDF5 can be built without MPI, as I mentioned. So let's install HDF5 without MPI. And fortunately, there's no user MPI on these, so we can use the tilde syntax. And we'll see we reused lots of dependencies, everything except for the top level HDF5 itself. We had to rebuild that without MPI. But turning off MPI isn't the only thing we might want to do with it for HDF5. We also might want a different MPI implementation. Okay, so there are builds done. MPI is not a package, really. It's an interface, and lots of packages provide that interface. So we talk about those as virtual dependencies. So a package like HDF5 can depend on MPI, even though that's not a package. And then other packages, OpenMPI, MPitch, and MVAPitch2, Intel MPI, provide the MPI interface. And any of these providers can be requested for an MPI dependency. So for example, we can build HDF5 depending on MPitch for the MPI support by saying Spack install HDF5. We're going to build with the high-level libraries. That's to set up for what we're doing later. We're going to say plus MPI and with MPitch. And the virtual packages can also be versioned. The MPI interface has different versions, and we could specify we want, you know, MPI at 3 or whatever in the spec syntax. But here we go. In this case, we've just swapped out mpitch for OpenMPI, and you can see, you know, all of the lower level dependencies were reused, but now we're building mpitch and the top level HDF5. Are there any questions that I should take now? Oh, this came back. I'll stop for questions in a second. Let's first check what we've installed. So if we check on what we've installed, right, we saw Perl. That one took a second to unpack. If we scroll up, we can see here's our 2 HDF5s with different MPIs and our HDF5 with no MPI. So here we're seeing a tree representation of the dependencies, but it's actually modeled internally as a directed acyclic graph. If we want to see the full graph, we can use the Spack graph command. So this last build we just did, we can Spack graph HDF5 plus HL plus MPI, depends on mpitch. And we'll get a nice colored ASCII graph of all the dependencies. And for something like HDF5, right, you can see, okay, HDF5 depends directly on zlib. It also depends on zlib through libxml2, which it depends on through mpitch, etc. There's also, if you were looking closely at this Spack find output, we'll see some things in here that don't show up as dependencies of HDF5, but we didn't install, but came through the HDF5 build. And these are build-only dependencies. So we haven't been modeling them as part of the runtime dependencies of the package. We're not linked against them, but we did have to build, you know, auto tools or CMake or whatever along the way as part of the build. So HDF5 was a little more complicated than the zlib and tickle that we were playing with earlier, but HDF5 is still, you know, reasonably easy to install. If you give that to, you know, someone with some basic experience and say, hey, can you install me HDF5? They can probably get it done manually pretty quickly. So let's look at something more complicated. Let's say Spack install Trilinos. And this is going to take a minute because Trilinos has a lot of dependencies. I think in this configuration that we're building, it has 23 top-level dependencies. We got to reuse some things from HDF5, but here we are. Open BLAS. All right, so this is where you really start to see the power of Spack. Trilinos, we like to pick on a little bit because it fits a very common category of HPC software that is incredibly difficult to get installed and configured correctly, and so useful that lots and lots of people use it anyway. And so people spend a lot of developer hours figuring out how to get Trilinos installed. So useful that lots of and so here, you know, it's going to take us about 3 to 5 minutes to get this installed from a binary. Depending on the system, it would take about 3 hours using Spack to build Trilinos and all of its dependencies on, a single node of a reasonably powerful sort. And I've heard estimates that it would take 3 weeks for a reasonably experienced person who hadn't dealt with Trilinos before to get Trilinos and all of its dependencies installed. So that's really the power that we have in managing all of those dependencies, automating the builds, and Spack already knows how each of these configurations needs to be built. Spack also manages consistency within the DAG. So HDF5, is a simple package that depends on MPI, but Trilinos has many dependencies, all of which depend on MPI. And Spack will ensure that there's only one MPI in the DAG. So if we build Trilinos again and we tell it to build with our HDF5 that we built with mpitch, so that's Spack install Trilinos with HDF5 support, depending on HDF5, here's the one we built before. This is why we built with HL, because Trilinos needs it and we wanted to reuse this later. And built with mpitch. This isn't just going to build Trilinos with mpitch or just build HDF5 with mpitch. Everything in this configuration that depends on HDF5 is going to be, or everything in this configuration that depends on MPI, not HDF5, is going to be built with mpitch. And these are some very bare bones configurations of Trilinos. We can see when we're done installing this, we'll run the Spack find command, and we can see exactly what we installed. But we'll also run the Spack find -v command, which will show us what all the options were on Trilinos that we could have changed and might add some other dependencies. So, any questions that I should handle kind of collectively out loud, Todd, or are we good on the questions front?
It's pretty quiet, so I think you can go on.
All right, well, we'll just wait for Spack to finish extracting this Trilinos binary. And there it is. And now we're ready to go. We can say Spack find Trilino or -d Trilinos. And we can see, exactly what it was built with. And we can say Spack find -dv Trilinos. And you can see there's a lot of options here. We picked the defaults for all of them. But, in another build, we might want to turn any of these variants on or off. So we mentioned before, Spack find kind of shrinks down some of this information. We can show the full graph with Spack graph Trilinos. And this ASCII graph will be accurate, but at a certain point, these get a little bit hard to read. So we also have the option to use dot. You can say Spack graph --dot Trilinos, and you can, pipe that to graph is and create a PDF. Oh, I don't have dot installed. So to avoid trying to go through X11, I'm not actually going to go back and install dot and do this because we don't have a good way to view this PDF over SSH anyway. But just know that that's an option, and the pretty graphs that Todd's shown on the slides all come from this command. So now we've installed a bunch of stuff. Probably not all of it useful. Certainly not all of it useful. We've just been playing around with the spec syntax. So let's go and cull some of these things we don't need. So this will be how we uninstall packages. So if we do a spack find -d tickle and a spack find zlib, we can see we really probably don't need all of these. So we can say, yeah, we don't need zlib built with an older GCC. Spack uninstall zlib %gcc at 6.5.0, right? So that's % for compiler, @ for version. This is the same syntax we use to install it. And we can say, yes, we really do want to. And there we go. And spack find -lf zlib. We can see that that one's gone. We can also uninstall things by referring directly to their hash. So maybe we don't want this older zlib built with Clang. Instead of figuring out what spec we need to specify that one, we can just say spack uninstall zlib /hxo, the one with the hash hxo. And Spack will say, no, you can't do that. You built a TCL against that, and I'm not going to uninstall that because it would break TCL. So there's a couple options. We could uninstall. We could say, okay, never mind. We want to keep that. We could uninstall it and all of its dependency, and all of its dependents, and that's what we're going to do. We're going to say recursively uninstall it. Yes, I'm ready to uninstall those two things, and they're both gone. So Spack also won't uninstall something that's not sufficiently specified. If you say Spack uninstall Trilinos, Spack's going to say, you have 2 Trilinoses. I'm not just going to go uninstall them all. Which one do you want to get rid of? And we could say, just get rid of them all. We could be more specific, but the easiest thing is to give the hash. So we want to uninstall the thing with this hash. And you'll notice earlier I said zlib /xho. In this case, I'm leaving off the Trilinos. It really doesn't matter which you do. Once you specify the hash, you've specified the hash, so Spack knows what package it is. But a lot of times, people find it easier to specify the package name. Just makes the command make more sense. It'll make them know kind of what they were doing when they go back and look at it. And yes, we'll uninstall that. So we've used the spack find command quite a bit already, but there are some advanced spack find features that we haven't talked about yet. So for example, spack find _mpitch. So this is what we call an anonymous spec. Right, there's no package listed for this, just a constraint on a particular dependency. And so this will give us everything, regardless of what package it is, if it depends on mpitch. Similarly, we could use the anonymous spec CPP flags equals -03 to see our optimized builds, well, our optimized build that we've done, but it would show anything else with the same compiler flags as well. So this is very useful for querying with the spec syntax. We can also look at implicitly versus explicitly installed things. If we just run Spack find right now, we get this huge list, and most of these are packages that we haven't expressed any particular interest in. They just came through as dependencies of something else, in most cases, Trilinose or HDF5. So we can restrict to the explicit dependencies using Spack find -x. And we can also query the paths that these are installed in with -p. So Spack find -px, and you can see now we've only got, the 3 HDF5s that we installed, the patch elf that Spack installed to explicitly to be able to handle the binaries, the 2 tickles we have left, the 1 Trilinose we have left, and the 3 zlibs that we installed explicitly that we have left. There might be some implicit zlibs around as well. All right, so that's a lot of the Spack basics. The one last thing to cover in this basics section is compiler management. So we used several compilers, but we didn't really query what was available. We just used them because I was leading and I knew what was here. If we run Spack compilers, that's an alias for Spack compiler list, and that'll show us what compilers we have available. We've used all 3 of them. The compilers are maintained in a YAML file. If we did the configuration section of the tutorial today, we would go over a lot more about how to configure that. But you can also modify it from the command line. So if we wanted a GCC 840 compiler, we can install our own. Spack install GCC at 8.4.0. And it's important to note that installing GCC is not the same as making it available to Spack as a compiler. So this command will install GCC. It's not going to change what compilers we have configured as available. It's just going to mean there's a package installed named GCC. We're going to have to also explicitly tell Spack to add that compiler to make it available as a compiler. And the reason that we separate the installing from the configuration of compilers is because compilers are often very complicated builds, and most of the time we don't actually want to install new compilers just because we made a typo on the version of the GCC that we want, right? If we have GCC 840 and I accidentally type 8.4.9, I don't want Spack to go start installing a new GCC and take over an hour. I just wanted to say, no, you don't have that installed. Here, try again. So here we can see we've installed all of the dependencies for GCC. And we're working on extracting the GCC tarball. GCC is another big one, like we saw with Perl and Trilinose earlier. But with a binary, it's going to take us, just a couple of minutes to install it. So the next thing that we're going to do once this finishes installing is we're going to actually add it to the configuration. So we're going to query its path. We saw the Spack find -p option earlier. We can use that to get the path. Spack find -p GCC. But we can also use Spack location -i, which is better for scripting things. Location -i GCC. And so we can say Spack compiler add. And there's 2 ways we could do this. We could add this GCC to our path, and then we could run Spack compiler add, and it'll search our path, and we'll find it. Or we can give it an explicit path to search. We can say search in Spack location -i GCC at 840. And we can see here's the YAML file that we've modified. We've added this compiler. Here's the YAML files that we have compiler config in. It's just this one. And now we can say Spack compilers, and we'll see our new compiler is available. And we can also remove a compiler. We can say Spack compiler remove GCC 8.4.0. Make sure you do this because other sections of the tutorial are going to assume the default compiler is 7.5.0. And since the default is the newest GCC, we really do need to remove this to keep going with the later sections. But we can see removing it is not the same as uninstalling the package. Spack find GCC, it's still there. And so it's very easy for us to add and remove compilers once we have them installed, either natively on the system or through, facilities staff have installed them for us, or we can install our own if we need to. So that's the Spack basics section. Next, Todd is going to talk a bit about some core concepts in Spack. We touched on some of these things kind of in passing to deal with some Spack basics. But before we go on, it's good to have some more common terminology and understanding of what we're doing under the hood that'll help you understand the later sessions. So Todd, back to you.
All right, thanks, Greg. I'm going to share my screen. My internet's been in and out, so if I drop out in the middle of this, that's hopefully that won't happen. You got to stop sharing, Greg. We got your whole screen. All right. Share this. Okay, so Greg covered most of the basics of installing and removing things with Spack and of customizing installations. And probably the key takeaway here is that if you want to do combinatorial versioning, if you want to install lots of different versions of things like the 7 versions of zlib or different versions of Trilinos that we did, Spack is really the tool for doing that. Other tools like your system package managers and things are really designed to manage a single stack. And so you've got one installation of every package sort of in a single prefix like /user. And all the libraries go into there. If you upgrade the package, the upgrade replaces the old version, so you can't continue using the old version. And you don't really have the same flexibility that we give you with Spack. Port systems are similar, so Mac ports, Homebrew, Gentoo, all of those things are really also managing a single prefix, and there's not a lot of support for versioning. The systems don't know that there could be multiple installations of different packages. And virtual machines and containers are if you use the package manager that's in them, are similar. So Spack is really providing this sort of combinatorial versioning capability, the ability to manage lots of different versions for either development or deployment over the other tools. So how do we do that? What's really going on under the hood here? If you look at the way that Spack manages packages, each unique configuration, each unique dependency graph is a unique configuration. So like if you think about this as the graph for MPI leaks, so it depends on call path, it depends on an MPI library. It has dynins, libdwarf, and libelf. And if you imagine that there's metadata on every one of those nodes, what we're doing in Spack is we're really taking that whole graph, some description of it that's complete and canonical, and we are hashing it and producing these little SHA-1 hashes that are base 32 encoded to identify directories. And so basically, and if you tweak anything in this graph, so if you tweak libelf or change parameters for any of the different pieces of it, the dependency or the dependence of that thing will also change their hash. So if you change the hash of MPI, but keep the hash of dynins the same, if you change their configuration so that their hash changes, then that's going to propagate all the way up. Call path built with a different dynist is different from call path built with another dynist. The MPI leaks built with a call path built with some new dynist is different from the one that was built before. So basically, it's Merkle graph semantics or Merkle hash semantics we try to make sure that every configuration gets its own install prefix. So this MPI leaks node gets its own directory, call path gets its own directory, and so on. The other thing that we do in Spack to keep things sane among the installs is we make sure that every package knows where to find its dependencies. So you may be used to systems where you sort of have to remember what MPI you built with when you run. So like if you build with mpitch, then you have to load the mpitch module before you run, otherwise things explode. With Spack, that's not true. We make sure that every library has paths to its dependencies embedded in it via rpath, which is part of the ELF standard. And that just tells the dynamic loader to go and look in these other directories for the libraries for the things that it builds. And so the thing that we're trying to preserve there is that we want things to work the way you built them. We don't want you to have to remember when you get around to running your program all the different dependencies of it, because there's just too many to manage. So the other thing that Spack can do that you've seen is that you can constrain versions of dependencies. So if you do Spack install MPI leaks with the Intel compiler, and you know that the version of libelf that we give you by default is breaking things or something like that, you can customize that. You can say, okay, well, I really want libelf at version 0.8.12 instead, because I know that's what's breaking my build. So I'll specify that on the command line. The cool thing about this is that you don't have to know the overall structure of this graph. You just have to know that libelf is in there somewhere. And so if you write that on the command line, it says, okay, well, make sure that the libelf version that I'm building is the one that I want. But you don't have to know, for example, that MPI leaks depends on call path, depends on dynasts, depends on libdorf, and that's how you get to libelf. You just need to know that it's there. So we guarantee you for any given graph that there's only going to be one version of each of these dependencies. We won't have something set up sort of incorrectly where, like, say, libdwarf points to one libelf and dynast points to another, and they're inconsistent and incompatible, and we accidentally load one that conflicts with the other. We make sure that that's consistent. So that's another thing that Spack does for you. Make sure that your graph is consistent. The other thing that we do that's a little different from other systems is we handle ABI incompatible interfaces, and they can be versioned like MPI. So you may have noticed that we're showing this MPI leaks graph. And you can see here that MPI leaks and call path depend on this MPI node. What actually happens when Spack resolves that, you saw with concretization, that things were being built with like OpenMPI and with mpitch. The packages are written to depend on the MPI interface, but when Spack concretizes the spec, it has to choose an implementation of that interface to actually build. And so what's going at 1.9, you could do that.
Todd, just so
Yep.
you know, you cut out for a moment. You may need to repeat your last sentence.
Oh, sorry. Yeah. So the packages in Spack are written I'll turn off video to see if that helps. I think my internet connection is not that great here. So let me stop video there. The packages are written to depend on a particular interface, not to depend on a particular implementation of the interface. So you saw that Trilinos, when we built it, it got built with OpenMPI or it got built with mpitch. The package itself is written to depend on MPI. And then during concretization, we have to swap in an actual implementation of this to make sure that we can actually build it. The cool thing about that is that you write the package once and you can build it with lots of different MPIs. That's the whole parameterization thing. And then the cool thing for the user is they can use the same syntax. So Spack install MPI leaks depends on mbapitch at 1.9, or Spack install MPI leaks depends on OpenMPI at 1.4 or higher, to install a specific version of MPI that they want. And if we did the configuration section today, and you'll see this a little bit in the environment section, you can customize the defaults for these things. There are a lot of preferences in Spack that let you sort of tweak the way that the concretizer chooses virtual package implementations like MPI here, or versions of packages, things like that. You can specify your preferences. So the other thing you can do is you can say, I just want MPI leaks with an MPI2 implementation, if that makes sense. This is not something your user would typically write on the command line, but this is something that packages frequently write. So if you know that you need, say, some of the routines in MPI3, you can say that your package depends on MPI3 or higher. And if you know that you need, just MPI1, then you can say that in your package, and we can choose a wider range of MPIs to support that. So we talked about concretization a little bit. You saw what it was doing in the basics tutorial. What it's really doing is it's taking sort of an abstract specification for a package like this with a few constraints, and it's filling in all the configuration details where the user is not explicit. And so if you ask Spack to install MPI leaks with the call path library at version 1.0 plus debug and libelf at 0811, what it does is it normalizes that spec, and so it builds out the graph and puts the constraints on the graph for you. It knows all the dependency relationships from the package recipes in Spack. And then the actual concretization process takes these hard constraints that you got from the command line, and it picks versions and variant values, and basically it chooses a value for every parameter that it knows about on the spec to come up with a concrete specification. So here you can see that for every node, we've picked a version, we picked a compiler, we picked a compiler version, we picked an architecture, and we picked variant values for all the variants and so on. So basically nothing is left for the build recipe to decide about how the configuration should work. The solver does that, or the concretizer does that. And so once we have that, every time we install a package, we also take this specific configuration and we store it in the directory along with the package, so that you can remember all that provenance. You know where the package came from, you know what it was built with, you know all the options. And so you really do have a lot of ways to build lots of different configurations and to sort of remember them. You can think of Spack as sort of a database for package configurations. It turns out this problem is actually NP hard. So if you really want to get into the details of Spack, a lot of the work that we've done recently on the tool has been in the area of building solvers for this kind of system and for modeling all the types of constraints that can be on HPC packages and all the types of optimizations that we would want to do to get sort of better dependency, better concretizations. And so we're not going to get into the details of that here. But just remember, this is sort of the core of Spack, is turning your request into a concrete thing that you can install and then feeding that into a build recipe so that it can actually be built. Like you saw, you can use Spack spec to see the results of concretization. This is basically a way to see what the solver is going to pick before you actually install. So you can play around with this, tweak things on the command line until it looks the way that you want. And then you can install the package once it looks like you want it to. The other thing that Spack does is it tries very hard to ensure that you get the dependencies that you said you wanted. One problem with builds on supercomputers is that they can be very sensitive to environment variables. So if things are set wrong, say like in your LD library path, or if you set a compiler variable the wrong way, it can sort of leak into your build, and it can cause you to get an inconsistent build. And so what Spack does for everything that it installs, every build gets a separate process, and every build process has sort of this environment set up where we set all the sort of build sensitive environment variables for you. We override your package config path, library path, and CC, CXX, F77, FC. And we point those at our own compiler wrappers. And the cool thing there is that enables us to inject include and library search directories as well as our paths into the build. So this is how we ensure that when we build a library, that it's going to be pointing to the dependency that you want it to point to. So essentially, we set this environment up. We have CC set to Spack CC, which is our wrapper. It's actually named the same as the compiler that it points to. There's a sort of Spack CC environment variable that points to the real compiler, and then when configure runs, it picks up this CC and it points to these wrappers, which then delegate to the real compiler. So you're in this sort of sandboxed environment that's overriding a lot of things about the build. And it's kind of cool because oftentimes in a Spack build, because we inject these includes and search paths for your dependencies, it looks to things like configure, like the libraries are already installed in the system. So sometimes if you build in a Spack environment, you actually don't have to put as many parameters on the configure line as you would in a normal build. You can omit some of them because of the wrappers. Because we inject this R path, the libraries are created in a way that they point to their dependencies. And that sort of persists throughout the build process until we actually finally install the libraries. And that's how we make sure that they know about the connections in the graph. Not every package adheres to this sort of single prefix languages. Sometimes these things really want to be installed.
Todd, I'm so sorry. It happened again. You might need to
okay.
repeat your last sentence.
Okay. So for Python, we have some special support. I'm not going to get too much into this because we don't use this all that much anymore. In Python packages can say that they extend the Python interpreter. And we'll get into this a little more in later sections, but basically for Python, there's this thing in Spack called activation. And so if you install, say, this NumPy installation kind of wants to be in the site packages directory of the Python installation. So we have this activation option in Spack that you can use to ensure that that happens. So if you install Python and NumPy and you really want the users who module load Python to see NumPy every time they do that, you can say activate NumPy in the Python interpreter and that'll link it in. And so we make a symlink tree of all of the NumPy directories into the Python interpreter, and it's sort of on by default. We are moving towards
Todd, I'm not sure if you can still hear me, but I don't think we can hear you anymore. Todd? Just checking. Greg, are you still there?
Yep, I'm still here. I am
Okay.
grabbing the PowerPoint so that I can continue from where Todd left off. If he doesn't reappear faster than I can grab the PowerPoint.
All right. Well, he just fell off, so I'm assuming his internet decided to have a day.
Okay. Let me grab where we were. And view. Okay, and if I share my screen. All right, and
we can see your screen, so you're good to go whenever.
okay. Play from current slide. All right, so Todd was saying we have this mechanism to link Python packages into their Python prefix, but we encourage people to use Spack environments instead. We'll talk about environments more later. But the reason that we don't encourage this as the primary mode is that you can only have one NumPy linked in this way, and every user of this Python is stuck with the same NumPy. This kind of restricts the combinatorial build space that we're trying to help users navigate. Ideally, you want to be able to use any of several versions of NumPy with a given Python installation. And you can do that by having separate Spack environments with Spack views, all things that we'll talk about later. You can also do it just by managing Python path, but managing environment variables often isn't the best solution. So another important feature that we haven't talked about is that we can build against externally installed software. And so on the left, you see an example of configuration that you could use to say, hey, Spack, I know you know how to build OpenMPI, but someone at my facility also knows how to build OpenMPI, and they know our systems, and they built some really good optimized OpenMPIs over here. And often, that's actually what we want in HPC. We don't want to build our own OpenMPI. Facility staff build those for us. They have the expertise in what MPI we should be using with our network. And we just want to build against that. So what Spack does is you have that external, and Spack just prunes the DAG there. So we say, okay, instead of this whole tree of OpenMPI depends on HWLoc, depends on libPCI access, none of that matters. We have our OpenMPI. We don't necessarily know what it was built with, but we know it's there. It's an external. It's already installed there. We don't have to worry about it further. When we do the configuration section of the tutorial, we go into more detail on how to do this configuration. But that section's kind of dry because it's just here's how you format a YAML file. Suffice it to say, you can configure Spack to use external packages, not just MPI, but anything that you want. Spack also supports custom repositories, external package recipes. So sometimes you use this because you have packages that you can't release publicly. Sometimes you have bizarre custom builds, or sometimes you just want to override something that's in the default repo. So these packages are composable. The external repository can be layered on top of the built-in packages. You can, you will search in your repository first and then search in the built-in if you didn't find it. The custom packages can depend on things from the built-in repo, and they can even inherit from packages in the built-in repo. If there's, something specific about how OpenMPI has to be built on your machines and you're the one in charge of supporting that, you might have a repo that has an OpenMPI package that inherits from the built-in, but overrides some attributes of the package. So this is a really powerful way to keep proprietary packages, pathological builds, and also just things you're working on, maybe that, the next step might be contributing back to Spack as an improvement. Spack mirrors. We've already been dealing with Spack mirrors from the basics section. Right, we used a mirror to access the binary, the pre-built binaries for the tutorial. A mirror can be local, it can be on a web server, it can be S3, anything addressable by a URL. And it is an archive of anything that Spack could need to download from the internet. It can have binary packages in it. It can also have source code, the resources, which are a Spack's way of getting kind of additional sources necessary for a certain configuration of a package. Patches that you fetch, all of that can go in a mirror. By default, Spack maintains a mirror in var Spack cache of everything you've downloaded, but you can host internal mirrors for, again, for proprietary software. You can host mirrors for air-gapped networks if you, create the mirror on a system accessing the internet and move it to the system that doesn't. All of these sorts of things mirrors allow you to use Spack without needing to go out to the internet every time. So when you use Spack, first it's going to search in its local cache, then it might search in some local mirror, right? So local cache, then a local mirror. Then it might search in the default Spack mirror. If you've noticed, for a while now, we've had a default mirror for kind of everything that Spack knows about that we set up in AWS. And then only if it can't find the package in all of those places, it'll go out to the canonical location on the internet and grab it for you. So that's all for the basic or the Spack concept section. We're going to talk about environments next. Tammy's going to lead that section, but I think we are scheduled for a 30-minute break first. So we're about 3 minutes behind. No need to make that up in the break. We'll make that up in the later sections. So we will be back at, this is nominally run on Eastern time. So we will be back at noon 03 Eastern time to continue with the environment section.
You can, the next slide should have the right information on it.
No, it doesn't, because I grabbed the copy that I had already downloaded from a previous tutorial.
Okay.
So I will stop sharing and see y'all back here in half an hour.
Thanks, everybody.
I have resumed recording whenever you are ready to get started. Ooh, we cannot hear you.
Hear me now?
Now we can.
Yay. So do we want to give people a couple of minutes, or since I've practiced this and I take more than 45, maybe I should just get started.
Yeah, I think we're good.
Okay. All right. So welcome to the environment segment of the Spack tutorial hands-on. At this point, if you've had the opportunity to go through the basics installation tutorial, you'll know that we have covered how to manage your Spack clone or your Spack instance. I'm going to call it Spack instance. Now, before I proceed, if you have not actually gone through the basics installation tutorial and you're just joining us, we do have some commands up here at the top where you can clone the Spack repository. You can set up the environment and type Spack tutorial so you can get started. So as I said, we have covered the 3 core commands, well, a few more than that, but 3 core commands for managing your Spack instance. In this section of the tutorial, we're actually going to introduce how you can use Spack environments. And these are kind of virtual Spack instances that allow you to aggregate independent groups of packages separately, but allowing them to share those common installations in your Spack instance. So what we're trying to accomplish here is to provide virtual environments similar to other commonly used tools like Python virtual environments. And why do we want to provide that? Well, it allows you to actually do a number of things, such as you can establish, suppose you work on multiple projects, you can establish some standard software requirements for each of the packages. You can set up run environments for your users, or maybe you've got a side gig and you have a development environment, but you want to have one Spack instance. You can set up packages for continuous integration. And because of the way we track Spack and the environments, you can actually use the associated files to reproduce the build. So you can reproduce it on other machines, or you can share those files with others and they can reproduce your builds on the same or other machines. And we'll go into that more shortly. So what are we going to cover in this section of the tutorial? Well, we'll go through the basics of creating and using environments, talk about how to add packages to them, remove them, how to modify the configuration, how to build the software in your environment, also how to use the software in your active environment. We'll talk about the two different kinds of environments that Spack supports. There's a managed or named environment and an independent environment. And then we'll go into a bit more detail about how to reproduce builds with the environment files. So let's go ahead and start with Spack find. Oh, and I forgot to ask, can everybody see the text? Do I need to enlarge it?
It is a little small. You may need to make it a smidge bigger.
How's that? Tell me when.
Looks good.
Okay, on that side. And then let me, oh boy, let me go over here and see if I can get that enlarged. And okay, is that better on that side as well?
I think so.
Okay,
For the right-hand side, for the browser, make it like, keep hitting Command plus until it gets rid of the sidebar. I think it'll look better.
okay,
There you go.
okay, that's a good point.
Yeah.
It does look better. Okay, sorry for the sideline there. Now let's go ahead and look at what we have installed in our Spack instance. So we can do Spack find. And what we should see is something on the order of the 45 installed packages here, assuming you went through the basics tutorial. Your mileage may vary a little depending upon what command you actually ran. But what we see here is a complete list of what's in our Spack instance, but it could be a little cluttered if you're supporting multiple packages with these, or excuse me, multiple projects with these packages. Recall that we have some packages that are built with OpenMPI and others with MPI. We also have multiple versions of HDF5 and zlib using different variants. And so that, you know, sometimes it's good to just have an environment that has only what you need for your specific purpose. So let's go ahead and create an environment and activate it so that we can start working in an environment. So we do that with Spack env create. We're going to go ahead and give it a name. So let's just be simple and say my project. And what we see here is that Spack created that environment. It actually created it within our Spack instance. So of our Spack environments subdirectory, and it created a view for it. And it's very important that we have that view for our environments because that view contains links to the actual installations in our Spack instance. If you want to see what kinds of environments we have in our Spack instance, we can type Spack env list. And we see at this point, obviously, we've only created one. Now we can go ahead and activate that environment with Spack env activate my project, or you can use the shorthand Spacktivate. You can also add a -p option to have Spack pre-pinned the name of the environment to it. And so we can say Spacktivate my project. And let's go ahead and look and see what we have in that environment. So Spack find. You see that we are in the environment. There are no root Spacks and no installed packages, despite the fact that our Spack instance has 45 installed packages. And why is that? Well, we have to actually tell Spack what it should be adding to that. Now, if I hadn't used the -p option, you say Spack env status and see what environment you're in. So let's go ahead and deactivate the environment. You can do Spack env deactivate or despacktivate for short. And it helps if you type correctly, despacktivate. And we can see Spack env status. As I said, we can see that there's no active environment. Using the -p, obviously the pre-pinned environment name is gone. Type Spack find. And we can see we have all of the same packages that we had before because we're currently sitting in the kind of the default environment, if you will, of the Spack instance. So now let's go ahead and reactivate our environment. I'm going to clear. and start installing some packages in it. So let's Spack install Tickle. Let me know if I'm going too fast. So we see here that Tickle was already installed if you went through the basics tutorial earlier. And we can see that Spack actually updates our the My Project Environments view with those links to the actual installation. Let's go ahead and install Trilinos. And this may take a little while, but what we can see, or what we will be able to see, is that we already installed all of the dependencies in that first section of the tutorial, the basic section. We can see that the Spack convention of using square brackets with a plus sign to show which packages are installed, and it also shows us the path to those dependencies or to the installation. And we're going to go through the process here. Fortunately, we have it in binary cache. Otherwise, this would take quite a while to install. Excuse me. And I can't remember how many minutes this takes. Did anyone want to answer the question or bring up the question that was in the Slack channel real quick and address that, or no? Fill the void. Okay, never mind. So we see that Trilinos was installed. It did come from binary cache, and our view was updated. And we can type Spack find, and now we see that, excuse me, we have two root specs, Tickle and Trilinos, and that's because we explicitly told Spack to install that software. Our environment depends on being able to use that software. We can also see that there are 30 installed packages. So these are the dependencies as well as those explicit or root specs that we had. And so it's basically the merged dependency graphs of those two root specs, or the software that we wanted installed in the environment. Okay, so now that we have, I'm going to clear this, now that we have those two packages installed, since we have an active environment, Spack actually sets a number of environment variables for us, so we can just proceed to use that software. Otherwise, we'd have to use maybe Spack load or module load to set up the environment. So knowing that we have Tickle has a program, an executable Tickle shell, and you can check and see, make sure it's in your environment by typing Tickle shell. We can see there is the binary or the executable, and here it is in our My Project environment view. So let's go ahead and use it. Run Tickle shell and just type hello world or whatever you want to type, and it echoes back and exit. And so we can see that once we are in an active environment, Spack environment, we can actually, and typos and all, we can actually use the executables there. So I'm going to clear that embarrassing thing up and look at how we uninstall software. So, excuse me, you can actually uninstall software from your environment. So suppose you've been working along and you realize, we're not going to include that software in our project anymore. So you can uninstall it. But in order to demonstrate that, let's make sure we have multiple environments, because what we want to show here is that you can have multiple environments and uninstall a package that use the same software, installed software, uninstall a package from one, and it's not going to affect the fact that the other environment still requires it. And so let's demonstrate that. So let's go ahead and create another project. Let's call it My Project 2, because we're being very creative here. And we see we created that environment. We're going to Spacktivate My Project 2. And in this case, let's go ahead and install a couple packages. Let's Spack install. We're going to install HDF5. with the high-level library variant enabled, and we want it to depend on impitch. Now this should already have been installed in your Spack instance, and it's a matter of updating our view at this point. Oh, and I forgot to put the minus P, so we can see that I lost my prepended environment name. Let's go ahead and install Trilinos. And again, same thing, it's already been installed in our Spack instance, so this will be a matter of adding it to our environment and adding the links to our view. And we type Spack find. And we can see that we explicitly said for my project 2, we want HDF5, and it's showing us that we enable the high-level library variant. It is also showing us that we said we wanted Trilinos in our environment. And we can see, once again, all those 2 packages installed and all of the associated dependencies are installed. Now let's go ahead and uninstall. I'm going to clear, actually, let me Spack uninstall Trilinos. I'm going to add the -y option so I don't have to respond to the prompt. Trilinos. And it's basically removing it from our view. So if we type Spack find our environments view, we can see that now the only package that we told Spack we want in this my project 2 environment is HDF5 with HL and the high-level library enabled, and we can see the packages that are the associated packages installed. Now let's confirm that we haven't had an impact on our other environment. So let's activate my project, or Spack env activate my project, and Spack find. And we're back to, well, we see Tickle and Trilinos, and we can see that Trilinos is still installed for my project. So the fact that we removed it from my project 2 did not affect my project environment. Now, Spack accomplishes this by doing reference counting of the packages. So Spack would never have uninstalled that package unless there were no environments and no packages that depended on Trilinos. So at this point, we've been working with 1 package at a time. Spack environments allow you to actually install and uninstall. We can work with multiple packages, and we can certainly install many packages, in fact, the whole environment, all in one Spack install command. And this, one of the beauties of that is we actually support install level build parallelism. So assuming as long as your Spack instance is on a shared file system, you can run multiple Spack installs and actually have it Spack perform the builds of the software that's in your environment in parallel. So I encourage you to follow that link if that's something of interest to you. Now, there are actually 2 ways of adding specs to your environment. You can add them from the command line with a Spack add call, or you can edit the Spack configuration file directly, but we'll talk about that more shortly. At this point, let's start with the command line. So let's activate my project. And let's Spack add HDF5 with the high-level library, and depending on impitch, because we know it's already been installed and this won't take too long. Let's also Spack add GIMP. And we have both of those. So let's Spack find. Now we can see that not only did we have Tickle and Trilinos, now we have GIMP and HDF5 installed, and we have the associated. We do not have those packages installed yet, because all we've done is add them to the environment configuration file. Now, if we want to install them, we would type Spack install with no other options in the command line. Well, no specs on the command line. What Spack will do is automatically look for the spack.yaml file in the active environment, and it will start concretizing and make sure that it installs all of the packages that we had not previously installed. So we can see it installed into the environment, updated our view. We can do Spack find. And now we see we have not only the root specs, but the number of packages that are installed in our environment have grown. Now, suppose you're on a project and after a while you realize, we were using a provider of the message passing interface, say OpenMPI, which is the default for Spack. Suppose we were using OpenMPI, but gosh darn, now we want to use impitch for everything. You can actually change the configuration of your environment to prefer a different default MPI provider or many other configuration settings. And let's see how that looks. Spack, spec, hyper. So let's try and look at what the concretization looks like for that through the Spack spec command. This will take a little while. But what we see here, and here is that what Spack is using by default is OpenMPI for the provider, and we can change that. So we can do that by modifying the configuration. So let's Spack config get, and this is just going to list that configuration file out for us. And what we see here is this is actually a spack.yaml file. It has a Spack element, and it has the list of specs. These are those root specs that we saw in the Spack find. These are the things that we explicitly told Spack that we wanted installed in our environment. And we have the view, and the view is true, and that is critical. Now, before we proceed, make sure you have your editor environment variable. Before you set that, hopefully everyone knows how to set their environment or their editor environment variable. What we want to do here is we want to tell Spack for this environment, I want you to prefer impitch, and we accomplish that by modifying this environment. So we can use the command line Spack config edit. And what we can do here is we can actually, I'm going to be lazy and copy and paste. We can actually add this packages element, and we're saying all packages, and we're going to provide some, specify some providers. And in this particular case, we're saying for the MPI interface, for the abstract class or virtual class, we want to have impitch always be the default. So what we can do here is, I'm going to copy and paste this. And by specifying that, again, it's very important to keep in mind this is going to be the new default for our environment. So we can override the normal Spack defaults. Now, if we save this, we can type Spack spec hyper. And what we'll see is that the new MPI provider is impitch. It was OpenMPI, now it's impitch. And then we also see all of the associated dependencies. So we've only scratched the surface. As I said, there are a lot of options that Spack has, a lot of knobs that you can turn, and you can actually use that spack.yaml file, that configuration file, to modify a number of those settings. And so you're encouraged to look at the configuration section. I know for this particular Spack tutorial, we're going to skip that, but so I do encourage you to look at that so you can see the bells or the knobs you can turn. Now, as I mentioned before in this scenario, what we're looking at here is, my project decided I don't want to use OpenMPI at all. We want to switch completely to impitch. How do you do that? Well, we change that default, and we can tell Spack to concretize, we can force it to reconcretize all of the packages in our environment with the Spack concretize and force with the force option. Now, this is, as I said, going to tell Spack to go through our entire environment, look at all of the packages and make sure that they all are concretized with the new configuration. So we see as Tickle's not affected by this. We see Trilinos, however, is affected by it because it's using impitch now with a new concretization. The HDF5 with the high-level library is not affected because we had already told it we wanted to use impitch. And like I said, GIMP is not affected. So if we want to actually install these concretized specs, we would run Spack install, but that's going to take a while. So we're going to skip that for now, but feel free to run that if you want. So as I said before, we've seen how you can be in an active environment and run executables associated with the software that's installed in it. You can actually build software with that, and we're going to look at how we do that right now. So you can do Spack env status. We're in our environment, and I already knew it. If I had bothered to look at the prepended environment name on my path, we can type which MPICC, and again we can see we've got an MPICC in our environment, in a view within our environment. And one of the things that Spack does when you set up the environment, as I said before, is it sets a number of environment variables for us. And you can check that by env grep path. And you can see load library path, man path, you see make prefix path, package config path. So a lot of these get set for us, which is great. Now let's see how we can take advantage of that by basically creating and running a little program. So we're going to write, let's go ahead. Sorry.
Migrate part of.
I'm sorry, is somebody asking me a question?
Nope.
I think
Okay.
background noise.
Okay, so let's go ahead and edit this program. It's kind of your standard MPI hello world example where we have, we have to include the MPI header, standard IO, it's a C program. The little twist on this one is that we're going to actually take advantage of this program to look at what version of zlib is associated with it. So we're going to include the zlib header and have it out, have the first processor rank 0 actually output that. So let's go ahead, and I'm just copying pasting to save time. And I'm going to compile it in MPICC. Remember, we've got any of the installed software in our active environment will be in our path. MPI hello CC. Now, one of the things that has happened over previous versions is you actually need to take advantage of Spack to tell the program what the include path is. So you can use Spack location -i, which you should have seen in the basics tutorial. So we say Spack location -i, and that's what is the install location of zlib, and include. And then we can type MPI run for processes. And I didn't give it a name, so I'll just call a.out, and we can see that each one of the processes or the ranks report, say hello world, and they report their rank, and rank 0 actually outputs the version of zlib. It says it's 1 to 11. Now, how do we know it's 1 to 11? Well, we know it's 1 to 11, or how do we know that's right? Spack find zlib. Ah, nice if you type correctly. Spack find zlib, and sure enough, what we have installed is zlib at 1 to 11. Okay, so that's kind of the basics of how you can install software, configure in an active environment. You can use the software, use anything that's installed in associated with the installed packages. In terms of executables, you can readily use the you build software in that active environment. So how does Spack do this? Well, it actually maintains a couple of environment related files. There are two files. One is the spack.yaml file, and one is the spack.lock. Now the spack.yaml file is the abstract specs. Those are the packages that you want installed in your environment. And as we saw before, you can also have configurations. You can configure, override the defaults that Spack provides in that environment. And then the second one is the fully concretized specs of that environment. So we'll see what those actually look like. Because these are files, they can be stored in a repository, they can be versioned, they can be shared, they can be reused. So it's a very cool feature of it. Now, before we actually get to that part of the tutorial, let's talk about the two types of environments that Spack supports. There's one that's called managed, as I said before, and that's a named environment, or some people also refer to it as a named environment because you can just identify it by its name. And then there's also an independent environment. Both can be created with Spack env create. Named environments actually live within your Spack instance in var Spack environments. Independent environments can live someplace else, some other directory outside of there. And they're not named, and therefore Spack doesn't know anything about them because it's not within Spack's purview. So let's review kind of a managed environment. My project is a managed environment. My project 2 was a managed environment. Let's go ahead and clear this out. We can use Spack cd -e for the environment and tell it, I want you to take me to the environment directory. If I didn't have it actually showing here, you could pwd and see that, yes, it's my environment and it is in var Spack environments. Let's go ahead and ls this, and we see that there are those two files we talked about. There's a spack.lock and a spack.yaml. We can also see that we have two environments, my project and my project 2, and apologies to anyone who's colorblind and can't see the green, but my project is currently bold and in green to highlight that it is the one that is active, if we didn't actually determine that, for example, from our prefix. Now, what does that abstract specification of our environment look like? We can cat spack.yaml. And we can see that file that this should look familiar from that Spack config get or Spack config edit. It has, the configuration that we added earlier, and it has those root specs that we had. And it also, very importantly, says we have a view. We can also do Spack config get if you want to do that. Now let's look at how do we create an independent environment. So let's start by just creating one on our, let Spack create a brand new fresh one. So let's go ahead and go to the root directory, make things cleaner in our Spack instance, make dir code, cd to code, and Spack env create -d. In this case, you need to provide a directory, and I'm just saying, the current directory. And we see Spack very quickly came back, said it created this environment and tells us how to activate it. Note that it's an independent environment because it's identified by the path. Now we can ls in here. Spack created basically an environment configuration skeleton for us. We can cat that spack.yaml file, and we can see that we have the Spack element. We have an empty YAML list denoted by the open and close square brackets and a view. Again, very true. We can type Spack env list and see that we still only have 2 environments. So again, these are not, code is not a managed environment. Now we can go ahead and start adding packages that we want installed to this simply by opening it up in our editor. You can use the Spack config edit, or you can just use the editor of your choice and edit the file. I'm going to change the syntax here a little bit and have, let's add Trilinos and let's add OpenMPI. Now let's activate the environment. I'm going to go ahead and use the -p option. And one interesting cool thing I think is that you can now see, instead of having that managed named environment, my project active, the -p actually shows us, the directory. And that, we've told it we want Trilinos and we want OpenMPI. So let's Spack install this. Did somebody have a question?
Nope, you're good.
Okay. So Spack goes through, concretizes the 2 specs, and it basically, updates our view to show that those 2 packages have been installed. Now, just because we have installed the packages in that environment doesn't mean it can't change just as before. We can continue to add packages. So let's add, sorry, I'm going to go ahead and clear that. Spack add. So again, at the command line, just because we did it with an editor last time doesn't mean we have to do that. We can use, well, what did I do? I forgot the at sigil. Okay, so we can add. Oh, that's cute. I didn't mean to do that. I'm going to Spack remove that HDF. Sorry about that. So let's cat spack.yaml. And we can see that we have that HDF5 at 551 as one of our root specs because I told Spack, I add it, I want you to install it. Now I'm not going to actually install that. If you actually wanted to do it, you could Spack install. But what I do want to point out is you can use Spack remove to, as you saw just a little while ago, I could remove a package from that list. So I'm going to remove the HDF5 and we can cat the spack.yaml. And remember, we have not run Spack install, so what is installed in the environment has not changed, and we can confirm that with a Spack find. Okay, so the next thing I want to talk about is that spack.log file. This is that fully concretized environment. And it has all of the information that Spack needs to reproduce that build exactly on a similar machine. Well, what does that look like? Well, Spack does that because it keeps so much more information. It doesn't just keep track, as it does in the spack.yaml file, of the software you want in your environment. It actually keeps track of the hashes, the roots, everything in that spack.log file. Because it has so much more information in it, we are using JSON because it's machine readable. I mean, it's still human readable, but there's a lot to it. And you can check it out by doing a head -30 on spack.lock. Just look at the top 30 lines and you can see those root specs, the actual hash for the root specs. You can see the concrete specs. So Trolinos has the version, the platform, the architecture, the compilers, and more. And you're welcome to look at that, but it is over 1,300 lines compared to that very small abstract spec in the spack.yaml. Now we can use either of those files to reproduce your environment with the spack env create command. You can give someone the spack.yaml file, and what it will do is it will basically create an environment that knows that it wants to install that software, those specific packages, but it doesn't really constrain them. And let's take a look at what that looks like. So we can do spack env create. I'm going to go ahead and do a named environment. Don't want to create a new directory or anything. Let's call it abstract because we're being creative here. Spack.yaml. And so we can see, again, abstract environment. It is known by Spack, and we can activate that. So let's Spacktivate. Spacktivate. I'm going to use the -p and abstract. And we can see Spack find showing us that we gave that file or used that file, we're using it, and we know what the root specs are, but we don't have any installed packages. Now we're still in our same Spack instance. So technically Spack knows how those packages are installed, but we haven't told it to associate it with our environment yet. Alternatively, we can use the spack.lock file, remember, fully concretized. So let's spack env create concrete spack.lock. Helps if you spell correctly. And here we've created another named environment, and we can go ahead and spacktivate it. And it is active. And we type spack find. Now in this particular case, we actually told Spack everything it needed to know to reproduce that environment exactly. And we're already in the Spack instance, so it knew where to get everything at. It's already been installed in our Spack instance. So it created, you know, the root specs are open MPI and Trelino, so we didn't even have to type Spack install, right? Because we're in the same Spack instance, and it has all of the associated install packages. Now, one caveat is that the spack.lock file, unless somebody corrects me, I believe it is still, will only reproduce a build for the same, on the same type of machine. So there's still that constraint. Okay, so we've pretty much covered everything. We have provided a number of links for you. If you want to know more about setting up and building environments, we have a link to the environment reference docs, the configuration tutorial. As I said, we're not going to cover that today, but we do have a link for that. Spack stacks tutorial, if you want to make more complicated environments, for instance, having a set of packages that you want to build against different compilers, multiple compilers, you can do Spack stacks. That's explained in the Spack stacks tutorial. And as I mentioned before, you can actually build an environment in parallel, and we have a link to the install level parallelism there. There are a number of ways of using environments. There are developer workflows, which will be covered in the next section. You can also use environments for GitLab CI pipelines. The Spack uses them to basically check the pull requests and releases. You can use environments to create container images. And as I said before, the Spack stacks tutorial is a way of managing large deployments of software. And then finally, if you want some examples, we have a link to Spack Stack catalogs. There are many examples sitting out there on GitHub, so you can check it out on the Spack Stack catalog. So that's all I have. Thank you very much for your time and your attention, and I will turn it over to whoever is doing the next section on developer workflow.
Yep, thanks, Tammy. That'll be me again.
Tammy, would you mind unsharing your screen or stopping sharing? Thank you.
Sure, sorry about that.
All right, let me make sure I've got the right materials up. And I want the developer workflows tutorial. All right, and I will share my screen. All right, can you all see my setup again?
Yes, sir.
All right. So let's talk about how to use Spack environments for a developer workflow. And the key point here is that when we're developing software, we have a little bit different constraints than when we're just using that software, right? If we're just using software, we can Spack install it, we can install it in an environment, it's there, we're ready to use it, that's great. But we don't really need to go back to the build again, ever. As a developer, we probably need to go back and forth, install, build, test it out, you know, build, test it out, build, break things, build it again. And we want to be able to do that more smoothly than having to go through the whole install every time. So that's what we're going to be talking about here. So we're going to want to install from local source. If you haven't been following along, I've cloned Spack. I've used the Spack tutorial command to get on the appropriate branch for this tutorial and set up the mirrors. And the Spack install command we've used it a bunch of times. It'll go out to the internet, grab the source or grab a binary and install from there. But as a developer, we probably have our own source code that we want to install from. So imagine that we are all developers of SCR. SCR is a scalable checkpoint restart library. It's part of the Veloci project in ECP. Supports reading and writing checkpoints, handles MPI for internode communication for backups and things like that. And we're going to test out our changes to SCR with an actual application. In this case, it's going to be Max.io, proxy app for HPC IO workloads. And we've chosen these two in part because I used to work on SCR, and in part because they're very quick to build. We can go through the tutorial pretty quickly. So let's start by creating a development environment for this. So we're going to cd back to our home directory. We're going to make a directory. This is going to be for a Spack environment. We're going to Spack env. We're going to go to that directory, and we're going to Spack env create, and we're going to say -d for the directory we want it in. We want it right here. I need to source Spack again since I logged out in the meantime. Now I will be able to do this. Okay, so we can activate this environment. We could Spack env activate it, but we could also just Spacktivate it. It's an alias we've set up. And now for this tutorial, to get through things quickly, we don't want to worry about Fortran, so we're going to build these without Fortran. And we skipped the configuration tutorial. Just going to quit out of Slack so it stops showing up on my screen. But we're going to add some configuration. So one of the things you can do in Spack configuration is you can set what the default should be for the compiler, for certain variants, or for a certain packages variants, whatever. So we're going to say Spack config add in the package preferences section, which is packages. For all packages, we're going to set a default variant. We're going to say the default is to turn Fortran off. And now we're going to add to our environment. We're going to say, okay, what we want to build is Max.io plus SCR. And let's install this environment. So this looks a lot like what Tammy just went over, right? We've set up an environment. We've modified configuration in it. We've added things to the environment. And we've run Spack install to install them. This doesn't seem all that life-changing yet. So now the next thing we're going to do is we're going to set this up for development. So to do this, we're going to use the develop command. And what the develop command allows you to do is it allows you to tell Spack, I have this package that I want to develop. And you can either say, here it is, or please clone it for me from GitHub. And Spack will either configure your environment to point to your existing source, or it will go and clone the source for you and configure your environment to point to that new source. And every build you make of that package, once you've set that up, will use your local source instead. So I'm going to pause, not get too far ahead of ourselves for the moment. Our build's chugging along. We've installed a bunch of dependencies, and we were hung up on Python for a minute. That takes a bit longer. but now things are flying along again. KV tree is a component of SCR, so we're getting towards the top here. Same with rank string and SPath. And MaxIO needs Slurm, so that's why that's getting built. You can see in the script, we have embedded the DAG of everything that's getting installed here. So you can see kind of how far up the tree we've gotten. If we're looking at Slurm, it's probably under OpenMPI here. But here we're all the way up to SCR. Oh, this is a graph of MaxIO without SCR. With SCR, SCR is up near the top. Okay, and here's MaxIO, and we can Spack find and see what we've gotten. So now we're going to develop SCR. So we're going to say Spack develop SCR at 3.0 RC2. Now, one of the things to note about this develop command is you have to specify the version. You can't let Spack pick a default for you, because when Spack picks defaults, Spack's assuming that it can go out and get whatever source it needs for that default version. But in this case, you're saying I have the source, and Spack needs to know what version the source you're using is. Or in this case, the source to download is. And we can look at the environment. If we look for develop in it, we can see we configured it to use SCR at this version. Now, anytime we install from now on, Spack is going to add a special dev path variant to our SCR specs. And that's because if we're tracking the provenance for this spec, knowing what version it is isn't really enough, right? We're controlling the source code. Spack isn't controlling the source code anymore. We could do whatever we want to that source code and still call it SCR at 3.0. And Spack's going to record it's the thing from that directory in case we've done something really weird. Now, there's two gotchas with this. One I said already, you have to specify the version. The other is that you need to reconcretize, because Spack will have a cached concretization of SCR from before we set it up for development. We're going to need to reconcretize to get the new variant. So Spack concretize -F, throw out the old concretizations and reconcretize everything. And when that output starts coming, we're going to see everything's already installed, right? We installed this environment already, except SCR and SCR's right here, right? This is a new build of it with this new dev path variant. It's not the same thing. And the other thing that's changed is MaxIO, because it depends on that new SCR. So if we Spack install now, we're going to get new builds of just those two, and everything else was already ready. And you can see we got builds from source, because now that we've changed to depend on this particular directory, we don't have pre-built binaries for that. So now we've got source builds of SCR and MaxIO, and everything else came from a binary. And now the nice thing for developers about the develop command is that it starts to behave a little bit like make, where it will keep track of when your source was modified and know whether it needs to rebuild. So we don't have to control, oh, I need to overwrite a rebuild or whatever. We can just develop our code and Spack will rebuild it. So we can say, I'm going to export editor equals Emacs because that's where I'm comfortable. And now we can edit scr/source/scr copy.c. I promise I didn't try to make that a tongue twister for you. And to simulate our jobs as developers, we're going to say, come in here and delete the first semicolon we can find, because the first thing we're going to do as developers is we're going to break something somehow. And now we'll install again. And like I said earlier, Spack sees that we've changed the SCR source. We don't need to tell it anything special. It's going to rebuild it. And of course, it's going to fail because we killed a semicolon. So we could look at the build output to know what's gone wrong. We could use the Spack build env command to get ourselves a shell to experiment with it. We could source the build environment to get a build environment. But in our case, we know what's wrong. As brilliant developers, we know that the fact that we killed a semicolon probably was the problem. So with our great debugging skills, we have replaced the semicolon, and now we can install again. And Spack sees that we've changed the source code, so it rebuilds SCR and rebuilds all of its dependents for us. So now we have, with our modified source, we've got our modified SCR source, and we've got max.io built on top of that. So taking advantage of iterative builds in Spack depends a little bit on your build system. So if you use make, you're going to get iterative builds for free, right? Make tracks which files were touched when, and if you rerun the build after you fixed something, make is going to know which files it needs to worry about, which ones it can leave the same. Same thing with CMake, right? CMake does a good job of tracking which files were modified when. It doesn't update CMake cache.txt if the update would be just writing the same new information into it. And then it relies on make, and everything behaves nicely. If you have autoconf, it doesn't behave quite as nicely. Auto or configure will modify config.h, even if it's just putting the same information back into it again, which will force the whole build to be rerun. So depending on what type of package you're modifying, you will see different behavior of how nicely this feature works. But either way, Spack will manage for you when you need a rebuild. It's just whether those rebuilds will have to start from scratch or not, depending on what you've modified. Now, you can also be co-developing multiple packages, right? I mean, in the ECP project, lots of us do this. We work on some library, and we work on another library that uses it, or an application that uses it. And so we could say Spack develop max.io at 1.1. So now we're co-developing SCR and the application that uses it. And we can say Spack concretize -f. And we can say Spack find, all right, let's just Spack install real quick. This is going to install a new max.io. and we can say Spack find -v and look at the variance, but this is probably too much. We can also say Spack find dev path equals star to say anything that has a dev path variant, whatever it's set to. And we can see these are our two packages that we're co-developing. The other nice thing about this workflow is that we have all of the reproducibility of Spack environments. We can take this entire environment and ship it to another person. They can use our Spack.yaml, they could use our Spack.lock, depending on the system, and replicate our build process. So we're going to create another environment. We're going to cd back to our home directory. We're going to make dir devel other. We're going to cd to our new environment. We can copy the Spack.yaml file. We could copy the Spack.lock, but we're going to just copy the Spack.yaml for now. So now we've got a new environment, could be a new user. We're going to activate that environment. And now we can just run Spack develop. And what this is going to do is Spack has used caches, but in the default case would be going out to GitHub or GitLab or whatever we're using, and has set us up with local copies of the source for both of these. So we can say, okay, one developer, added a dependency, SCR, set us up to develop it in addition to Max.io, gave the environment to another developer, they just run Spack develop, and they get all of the packages that this group is working on. You can Spack undevelop something to say, okay, I'm done. I want to deploy this now. Spack undevelop SCR Max.io, and now I could reconcretize and reinstall Spack concretize -f. And now when I install, there will be no Spack install. Now when I install, there will be no dev path variant in any of these packages, right? I can search for dev path. There's no developed packages. All of these are installs from canonical source, but that canonical source might be including the changes that I made and contributed and pushed out into a release in the meantime while I was developing it. So to summarize, you can use the Spack develop command to make a reproducible build environment in your local Spack that you can share with other developers. You can iterate on the build using Spack install. It'll integrate with make to do iterative builds, and you can kind of rebuild the minimum number of Spack packages necessary to reflect what you've changed, keep working, share that work with others on your team, and then eventually, contribute your changes back and seamlessly transition back to using canonical source builds. So that is our developer workflows section. And any questions on that? I'm not hearing anything. In that case, I think Todd has some wrap-up slides for us at the end here.
We have 25 minutes left. So we actually finished early, which is pretty cool. So we could take questions from folks who want to talk about particular things. We could do, I don't know, I hesitate to do it because my internet is bad, but we could do the mirrors and the binary caches one, which I think people might be interested in.
Yeah, let's do that.
Chuck has a question though.
Okay.
So let's hear from Chuck, and then we'll maybe fit in mirrors since we have extra time, more than we thought. Chuck? We cannot hear you, Chuck.
Chuck, it's showing you as unmuted. It just seems like your volume is not coming through.
How about now? You get
Now we
I
can
heard
hear
you
you.
that time. Yep.
There you go.
Okay, yeah. Zoom was trying to auto adjust the volume down to nothing. That's not helpful. Thanks, Zoom. Okay, yeah, so this is kind of maybe in the spirit of mirroring, but I was wondering if you could speak at all to Spack chaining. A common developer workflow within ECP is that you're trying to develop on your Spack package in an environment that already has a Spack installation, but you need to, so you want to kind of use like an installation that maybe the facility has, but using, newer Spack packages for your own stuff. So I'm wondering if you could speak to Spack chaining at all for that.
Yeah, so that definitely works. Spack chaining. If we look at Spack config blame upstreams, right, we have none configured, but in this config section, and we haven't talked much about config sections today, but basically config sections are different YAML files. In this file, you could specify the location of an upstream, and the way packages are reused from upstreams is the same as the way they're reused if they're available locally, right? You concretize and you see the hash, and if that hash exists upstream, it'll use it kind of transparently rather than you having to build it for yourself.
Spack will also show you if you use -I with it.
Yeah.
That whether it's installed upstream or locally, so you can see what's being pulled from.
So if you do a spec -I, I'll just use zlib, right? You get a plus here. You'll get a caret here if it's from an upstream. So that works pretty seamlessly with the develop feature, because anything that you're developing is not going to match the upstream. But any of its dependencies, whether or not they match the upstream, is going to be unchanged. So you can get all of your dependencies that way. Obviously, you're going to have to rebuild your dependents anyway, and so the upstream isn't really relevant for those. Does that answer your question, Chuck?
The kind of workflow problem that I run into quite a bit with this, and I don't know if this is just a problem with Spack or if I'm doing something right, is when trying to specify an upstream, then you're kind of giving it where the installation of those packages are, but that doesn't really have any of the configuration to it that those packages were built with. So there's like I don't know how to kind of make sure that I'm getting the same kind of compiler environment that those were built with, or kind of what externals those were set up with, and that it seems like the kind of the installed packages are there, but kind of the rest of the pieces to effectively concretize things in that environment aren't, or am I missing that?
So everything that I've talked about so far has been features that were available in Spack version 0.17. The answer to your question is to use a more recent Spack. V0.18 is going to be released this week or next, but you could use, from the develop branch in between. And there's options now to turn on concretizer reuse.
Actually,
And-
reuse is in 0.17. You can do it with spec -- reuse. So you can do this. The
Okay.
reuse is better it'll be better in 0.18 because it has a few constraints.
and it
looser
will be
default.
and it will be the default. And what reuse does is, when I talked about how Spack reuses things, going back to the basics section, but all the way through to right now, I said, right, you concretize, you see the hash, and then you see whether it's installed or whether it's installed in an upstream or any of these things. And what reuse allows you to do is say, okay, generate the abstract constraints of what I need. And anything that satisfies those abstract constraints that I can reuse, I want to reuse. And so what Chuck asked about is exactly right. If you don't have the same configuration as the upstream, without reuse, it's really hard to reuse the upstream packages because you're going to concretize to something slightly different because you have some different defaults, some different preferences, whatever it is. And there wasn't a good way to kind of project those preferences down into what you're doing. One option to deal with that has always been to use the config directory option, Spack-C, and you can pass it a directory, right? So that could be, system deployment, Spack configs, or something like that. And that would get you partway there. But really what you want is reuse.
So I mean, if that install was created from an environment, then like separate config files for that was all from like a Spack YAML,
Yeah. Well, you can point to a Spack YAML as your config with the -C option also, but
Okay.
reuse is really what you want, right?
Okay.
Because what you want isn't so much, I want to concretize with the same preferences that they concretized with. You might not want the same preferences for the new builds that you have to do. What you want is, here's my preferences, but also I don't want to rebuild things I don't have to. So go use this stuff as aggressively as you can. And that's what the Spack, the reuse option does. And like I said, version 0.18 we're releasing in the next week or so. And it will be the first version for which that reuse option is the default.
Okay. Yeah, I think some of these things may help. It seems like they are more tied together than they used to be. So that'll be helpful.
Yeah, so keep in mind, it seems like people really want reuse. So we're moving towards it, and we're trying to maintain all the compatibility constraints that come along with that, which is hard. And so the trade-off is really that with reuse, you lose a bit of determinism because now your install is stateful, right? It's going to reuse what it can or what it thinks it can. But you won't, when you say install something, you won't get a deterministic hash for that when reuse is enabled. So there will still be the option to use the old install method where basically we only consider what's in the package files and your preferences, and that's called a fresh install. And so you would say spack install -- fresh, which is like the opposite of reuse. So I think, does that help a little more, or does that confuse things more?
It helps. So
Yeah.
I think
Cool.
yeah, that helps. I think in my mind, like an upstream install has a configuration that it's tied to, but it seems like those still need to be kind of explicitly specified separately.
Yeah, we've always wanted, so the facility may have installed a bunch of stuff, but we've always wanted the user installations that chain to a facility install to be able to customize what they do. And if when you allow that, right, then the user config can easily deviate from what the facility used. So it's been hard traditionally to get the hashes to match up unless you're very
Yeah, but I mean, it needs to start with from somewhere, right?
Yeah.
well, which is what reuse effectively is, right? Like we don't know all the configuration that was used to build every spec in an upstream installation. It could have changed over time or anything, but we do know what's installed. And so what we're doing is we're optimizing for basically reducing builds. If we can take a hash and use it instead of a build, then we will.
Mhm.
And that's and then we also spent some time getting getting that optimization correct, because like you tell computers what to do, right, and they do exactly what you say. So we said minimize the number of builds that you're doing, and what happened was that we got really weird installs of things that we had to build. So it would be like, oh, I'm going to build CMake, and it looks like you want to minimize builds, so I'll disable all the useful features like OpenSSL, this, so that, right, that require an extra dependency.
Yeah, not what I meant.
Yeah, and you're like, no, oh god. Yeah, so there's it's a little more complicated than just minimizing builds. It's bifurcated. If you have to build something and there's no other option, then we stick with the defaults like we used to, right? And so those will look the way that you expect. If you have installed something and we can avoid a build by using it and it satisfies all the constraints that you asked for, then we'll reuse it. So I think it's going to work pretty nicely, and it'll make using Spack a lot more pleasant when you don't have to rebuild as much. People have liked it since 0.17 came out, at least on Slack. They're like, oh gosh, this reuse thing is nice, because it prevented me from having to build 10 things, and that's great. So we're finally comfortable with turning it on default.
Okay.
In addition to reuse, the configuration in the long term, right? Configuration is currently associated with a user, and it's in the home directory. And in the long term, we want to move that configuration to be associated with an install tree,
Yeah.
rather than with a user.
Yeah.
This is longer term work, but what that will also do is that when you're using an upstream, the configuration, not necessarily all of the configuration used to develop it, right? Some of the configuration used to develop it could have come from an environment or from the Spack instance it's associated with. But the configuration that is actually associated with that install tree will also naturally be in your config scope.
Okay.
And we have to figure out exactly what that's going to look like. That's further off than 0.18, but that will be a change in the future that is also in this direction of getting the config from your upstream.
Okay.
I think Jim's had a question for a while, so I want to get to Jim. So Jim, go ahead.
Yeah, I mean, so you guys have been kind of bumping around my question quite a bit, but I was just gonna say that I recognize that reuse is less clear, and being the most clear tends to not have people being able to reuse. But yeah. I wonder how much value there could be just in having clear conventions around, like what Greg was saying before. Oh, you might find that configuration in /system/ something or whatever, not else. And it feels like, from the perspective of being able to reuse the system configurations, or even people who are trying to build additional things, having clearer conventions for communicating these things would be good. Sometimes people, know to find them in a set of configs, associated with E4S, or a set of configs that's in Spack itself, but sometimes they're not there, and sometimes they're not easily found at all, and it's just kind of, I don't know, luck is the wrong word, but like, do you happen to know where the set of configs for this particular facility tends to live? And so it's not even just the reuse case, but am I starting with a sane environment in which I can attempt to build something? I agree that the reuse case is huge, but and I feel like a lot of the message of reuse in that way, we're still trying to work on with some of the facilities, because traditionally they give you the stuff, you use the stuff. And this, like, I want to build a little bit of my own stuff, but use a lot of what you have. I mean, they have kind of distinct layers between these in the past, but it's more fluid with Spack now. You might want to just like take one piece and rip it out and do what you want to do. Anyway,
we have a couple things that may be interesting to you in the pipeline for that. One of them is Tammy's actually working on a feature that's it's not going to make it into 0.18, but probably in 0.19, where we would name configurations and we could refer to them by URLs. And so essentially, like in your environment, you could say include, I don't know, like E4S/defaults or whatever, and that's a repo in the E4S org on GitHub. And we could fetch the configuration from there. And so facilities could potentially publish their configs and name them, on GitHub as just regular old repos. And I think that would make it easier for people to say, like, include a specific configuration, because it would have a well-known name, as opposed to right now it's like, give me the file, which is super annoying.
I mean, there is also the Spack configs
yes
repo on GitHub, and we encourage people to post their configs as a directory or a branch there. I can't remember exactly what the structure is off the top of my head, but I think that's another thing to, if you're having trouble getting configs from a facility, maybe encourage them to post them there, because that's kind of the best form of sharing we have right now.
Yeah.
Yeah, and I want to be clear that I don't view the responsibility of establishing these conventions and getting people to put all these things. I don't think that's something that's squarely on the Spack team's shoulders. There's a lot more to it than that, and conventions at the different facilities. But I really think if we could do that, that would be an enormous productivity boost across the entire project.
Yeah, I mean,
we sort of originally
we want to make a way for you to talk about those things easily, and then I think the facilities can go nuts and make configs and hopefully name them well. But yeah, go ahead, Greg.
We sort of originally envisioned the /etc/Spack config scope as an opportunity for that, but it turns out the relationship between people deploying Spack at a facility and the people in control of root at that facility is usually not close enough. Maybe occasionally it would work to have that sort of set location where those things lived. So for the people that works for, great, but otherwise, yeah, I agree. We need better options for this.
It's also not clear that every facility has like one set of defaults. You may want to include the facility's Rockham settings versus the facility's CUDA settings, and those could be two different sets of configs. And so so naming them is way more flexible than the Etsy Spack scope that I stuck in 2013. So Matt, I think, was next.
There's a few things. Try to organize my thoughts here.
You want to let Igor go?
Well, I'll go back in reverse history order. So our site configs are generally in a standardized location in the file system, and I don't think that we do a great job of publishing where those are. They're also on public GitHub repo, and in Spack configs, the Spack/Spack configs. Although I don't think they're updated there quite as often as they should be. But they are available. And that reminds me what I originally raised my hand for. With reuse, this raises a question I don't think facility software deployment folks have talked much about or established a good policy on. I'm really interested in reuse. We do a lot of builds, but facility deployments are something that we expect users who want to use as upstream. And while reuse will save us from building or rebuilding a lot of packages that already exist, I guess I think we need to establish how often we should do a fresh rebuild. Whether
Yes.
that's per P4S release or per version of Spack, when we move to a new version of Spack. But I reckon that we want to, on a regular basis, rebuild everything so that what is installed is the latest at a certain point in time.
Yeah, and we will likely keep rebuilding fresh all the time in CI to make sure that the latest defaults work. So I suspect that CI configurations will always be fresh. I don't know what, yeah, like you say, like what a facility would do or how frequently they would want to make a fresh rebuild versus a reuse rebuild.
I mean, a fresh rebuild of the software stacks that we deploy on machines takes collectively for all of them days.
Yeah.
So we do want to reuse builds as much as possible, but right, I'm not that excited about indeterministic builds. So at some point, I think the facilities will have to make an agreement about how often.
I should say they're still deterministic in that the configuration is written down after reuse. So you could redo them and get the same errors. They're not deterministic in the sense that, you know, that someone could reproduce what you did without having the same install tree. Right.
And maybe that's fine. If there's a issue discovered with reusing a certain version, a certain configuration of the dependency package, that could be made into constraints on upstream packages as they're discovered, then when we rebuild a package, even with reuse, we'll get something that works for users and for the site. So maybe it's not a terrible thing, but it's new, so I don't have like a good sense of how everything will work.
I'm curious to know how you guys end up doing it, because or what you find, because I think it's clear what the advantages are for like end users who already have stuff installed, and that's why I think it should be the default. But yeah, like you say, I don't know what the default should be for a facility. Igor?
I know.
Oh, go ahead, Greg.
I know for facilities deployment at Livermore, we've talked about doing, you know, you kind of start the deployment for a machine and then you use reuse for the life of that machine to kind of keep what's on that machine smaller. But anytime you're starting fresh on a new machine, you use a fresh install for the first install there or something like that.
Yeah, when refresh was first added, we had issues actually reusing packages that we'd already installed. So as of this in the past month, we've done a full fresh build of everything. And well, I'd like to not rebuild everything that often if I can. We will see. Historically, we have rebuilt everything. We just reconcretize all the specs and how they are reconcretized, that's what we install. It's kind of what we're used to, but that does take time and disk space. Disk space really isn't that much of an issue, but the time is.
All right, so let's go to Igor because he's had his hand up for a while. We have like 1 minute.
Yeah, okay. So how do you deal with the situation when system libraries shadow what is supposed to be used? For example, if you build LLVM with CUDA support, then incurses from system installation is tried to be used instead of incurses built by Spack, and that creates problem. How do you deal with this situation?
So that really has to be addressed on a per package basis because it depends a lot on how the package's build system searches for these things. I don't know what the particular case is for LLVM with N curses, but for a lot of, For a lot of packages, it's as simple as, the package.py file in Spack turns on, -- with and curses. And it needs to set, with and curses equals, and then give the path of the Spack installation so that it knows to look there and not look in user local lib or user lib. But for some packages, they don't have an option to give it a path. And often for those packages, we end up having to write a patch in Spack to, it automatically looks in user local, and we have to kind of patch the value of the location of the ncurses library directly into the build. So it really depends on the particular case and what options in the build system are available. Is there a package config option that we could, set package config path to point at ncurses? There's all sorts of different things that could be the answer depending on exactly what is going on.
I would say it's probably a bug if we're doing that. So can you make an issue for what
I did make an issue like a month ago. I still
okay.
the reply.
And we should look at it.
But I encountered this problem with several packages. And by the way, with LLVM, I tried to uninstall the ncurses. Okay, that worked, but then I ran into the next package with the same situation. So I'd like to be able to do it somehow systematically.
So for example, there is a patch that is applied to our LLVM builds already called LLDB external ncurses, and is applied under particular circumstances. My guess is that something similar is needed under some other set of circumstances, but to solve the same problem.
Okay. Yeah, I ran into similar problem with caucuses as well.
Yeah, I believe it. It's probably one of our kind of most common things that we have to patch packages for, is that they assume that some dependency is always going to come from the system package manager and don't expose an option to say where it comes from.
So on that note, as a package developer, is that kind of then the best practice then is to always explicitly specify the location of where your dependency is coming from instead of assuming that Spack provides it in the right place?
It is better to do that, yes.
Okay.
You should pass the path into the dependency prefix. And similarly, to avoid spurious linking, you should, if there's a with or without option on like configure, if say the variant is off for ncurses, you should supply without ncurses to the build system so that it actually disables it, and you should supply with ncurses equals path so that it enables it when it's on.
Yeah. It may be good to have in the spec kind of some best practices instead of these are all the things you can, like there are some good practices to have.
Yeah, that's we should have that in the packaging guide, like some best practice up front. For this particular issue, we should also scan the neededs and the RPaths in produced libraries, basically run LDD on the whole tree and make sure there's nothing outside of Spack that we don't expect.
Well, I mean, I guess that's like any external you have that comes from /user will kind of bring that in. So
well, you have, so if the RPaths are set up correctly, then they should prevent, I mean, so for all the things that we put in /user, basically every external that you provide, if it comes from a system directory, that gets moved last in the list of paths, and we don't RPath system directories. So we assume that, so like /user, anything that would typically come from LDSOconf, we don't put in the RPaths. It's really only the Spack prefixes, like the one-offs, that we stick in the RPaths, and we make sure those come before the system prefixes for that reason, because system prefixes are a mess.
Yes. All right, great.
And how do I know if with ncurses option is provided? Would Spack Info show that, or it's deeper than that?
You would need to look at the build system and run configure -- help for auto tools, or I guess, so what's the best way to inspect the CMake build to see what it offers, Chuck? Do you run CCMake or what do you do?
Oh, that's a great question.
I used to run CCMake for this. I haven't found that CMake has anything that's as good as configure -- help.
Well, I mean, yeah, no, but in fairness, I think configure -- help. Yeah, no, there's not. Yeah, there's not a good option.
Yeah, I also will just edit the CMake list.txt at the top level to see what the options are, and look for option in it. I mean, that's my other go-to.
You can also, or what I often do is look at the CMake hash once it's done, see what all it's found instead of like digging through recursive CMake list.txt files.
Yeah, I mean, there's ways to find out. There's not as good of an option as like -- help. Show me all the tunables.
Yeah.
So
David Polyakov did once write a tool that would take a CMake list.txt and generate variants for every
there's-
single option in it, and it was awful.
there's reasons, and you know, but kind of the end of the day, like a lot of end users don't care about the reasons. They're like, why don't I have the thing that makes it easier? It's like, well, because reasons, but yeah, there's not right now.
Yeah, because build systems are unloved.
All right. We are out of time officially. So in interest of people having their full lunch break or being able to get to other tutorials or whatnot, I think we can close out, but I think I can probably speak on behalf of Todd and the rest of his team. If you have any questions, the Spack or the Spack Slack is always there and open for people to ask questions.
Yep, definitely. And hope you enjoyed the tutorial. Thanks.
Thank you everyone for attending.
Bye.
Thanks.
Bye.